Hello friends, we all know that one of the fundamental goals of physics is to investigate something that everyone talks about, that is energy. The topic is obviously important. Indeed, our civilization is based on acquiring and effectively using energy. We are surrounded by numerous energy interactions in our daily lives. When we eat breakfast in the morning, our bodies convert food energy into kinetic energy as we walk and to potential energy as we climb the stairs. When we start a car, the chemical potential energy stored in fuel is converted to electrical energy stored in the battery and used to power the radio, windshield wipers and headlights. We spend a tremendous amount of money to acquire and use energy. Wars have been started because of energy resources. Wars have ended because of a sudden overpowering use of energy by one side. Everyone knows many examples of energy and its use. But what does the term energy really means? Isolation and systems. To undertake the study of energy and interactions, we first need to define two basic concepts: open and closed systems and isolated and non-isolated systems. As shown in this figure, if a system does not lose or gain particles during the time of measurement, it is said to be a closed system. The non-porous boundary of this box prevents movement of molecules between the box and the outer environment. The inside of the box is therefore a closed system. Any other system, as shown in this figure, is considered an open system. With a porous boundary, the molecules of gas in the box can escape, while air molecules from outside the box can move in. In an open system, there is no way to ensure that the original contents of the box will remain the same. If a system does not exchange energy with any object or circumstance outside of its own boundary, it is an isolated system. Systems that exchange energy with other systems are non-isolated systems. A system is closed if the amount of energy contained in it is constant. In practice, a closed system is difficult to obtain. Nature adds and subtracts energy from a system in many ways, and most of these processes are not immediately obvious. But many systems lose only a small amount of their total energy, which allows us to accurately analyze energy transfer. We can illustrate the difference between open and closed systems using the example of two cars. Both cars are initially moving at the same speed. Car 1 puts its transmission into neutral and slowly rolls to a stop. Car 2 continues with its transmission properly engaged and its speed unchanged. Now, we will distinguish between these two cars from an energy standpoint. For car 1, the energy removed from the initial kinetic energy of the car is lost to the environment in different forms. The most common type of energy loss is due to heat, but energy is also lost in the form of sound and other types of mechanical energy such as air drag, mechanical friction and tire deformation as the car rolls. Ultimately, these forms of energy are also heat loss. In a closed system, energy is transferred from one form to another, but there is no energy transfer from a source that was not originally in the system. This constraint keeps the total energy constant. Therefore, for car 1, if we consider the car and the natural environment, then the system is closed since no energy is coming from a source outside our defined boundary. For car 2, energy is still being fed into by its engine. If the system boundaries we have defined are the same, then the system is open because chemical energy is being transferred from the fuel tank. However, if we broaden our system to include the energy in the fuel tank, then both systems, that is car 1 and car 2, are closed. The system would be open if the cars were being fueled. Thus, we must be careful in defining our system. The definition of whether a system is closed or open is a relative one. Work. Work is the transfer of energy. Work is done when a force acts on an object, causing the object to move in the direction of the force. Mathematically, work is the dot product of the force applied and the displacement. W is equal to F delta D, where W is the work done on an object measured in joules. F is the force applied on the object measured in newtons, and delta D is the displacement of the object in meters. In this figure, two construction workers are applying a force to the right. Worker A is pushing a wall that isn't moving, while worker B is pushing a wheelbarrow that's moving. Because work depends on displacement as well as force, only worker B is doing work. Worker A isn't displacing the wall, therefore, no work is being done on the wall. Worker B is displacing the wheelbarrow with his applied force, therefore, he is doing work on the wheelbarrow. So, we define work as work is energy transferred to or from an object by means of a force acting on the object. Energy transferred to the object is positive work, and energy transferred from the object is negative work. Work then is transferred energy. Doing work is the act of transferring the energy. Work has the same units as energy and is a scalar quantity. The term transfer can be misleading. It does not mean that anything material flows into or out of the object. That is, the transfer is not like a flow of water, rather it is like an electronic transfer of money between two bank accounts. The number in one account goes up while the number in other account goes down, with nothing material passing between the two accounts. Note that we are not concerned here with the common meaning of the word work, which implies that any physical or mental labor is work. As shown here, if you push hard against a wall, you tire because of the continuously repeated muscle contractions that are required, and you are, in the common sense, working. However, such effort does not cause an energy transfer to or from the wall, and thus no work is done on the wall as defined here. Kinetic energy. Kinetic energy is energy associated with the state of motion of an object. The faster the object moves, the greater is its kinetic energy. When the object is stationary, its kinetic energy is 0. As shown in figure, a force is applied to a crate of mass m, initially at rest on some rollers. Because of force F over time delta t, the crate undergoes a displacement of delta d. Because of the work done on the crate, its velocity increases from 0 to v2. Using our knowledge of kinematics and dynamics, we can develop an equation for the work done on the crate. Here, work is equal to energy and is equal to force into delta D and is also equal to m A into delta D. Here A is equal to V 2 minus V 1 upon delta T and delta D is equal to V 2 plus V 1 upon 2 into delta T. Since the force and the displacement are in the same direction along a horizontal line, we have omitted the vector notation. So, E is equal to m into V 2 minus V 1 upon delta T into V 2 plus V 1 upon 2 into delta T. Since V 1 is equal to 0, E comes out to be half m V 2 square. If we assume V 1 to be equal to V, then E comes out to be half m V square. The expression half m V square is the term for kinetic energy. Kinetic energy is the energy of motion when work is done on an object. Kinetic energy is a scalar quantity and its SI unit is the joule. Work and kinetic energy both have the same unit. Work energy theorem. As we have seen in the figure in the earlier section of our discussion, that since the initial velocity of the crate is 0, the crate has no initial kinetic energy. Once work is done on the crate, its velocity increases and it now has kinetic energy. The change in kinetic energy is caused by work done on the crate. Mathematically, E is equal to delta E k, that is the change in kinetic energy. We can write this as E is equal to E k 2 minus E k 1. Here E k 2 and E k 1 represent the final and initial kinetic energies respectively. The relationship is called the work energy theorem. The work energy theorem states that if the speed of an object increases, the work done on the object is greater than 0. That is, if V 2 is greater than V 1, then work done is more than 0. Conversely, if the work done is less than 0, then the object is doing work on the agent exerting the force. That is, if V 1 is greater than V 2, then work done is less than 0 or it is negative. The greater the velocity, the greater the kinetic energy of the object, which has constant mass. The kinetic energy varies directly as the mass and the square of the velocity. In other words, for a moving object, if the mass is doubled, the kinetic energy is also doubled. If the velocity is doubled, the kinetic energy is quadrupled. Gravitational potential energy. When we see a book shaking on the edge of an overhead shelf, or when we walk under a ladder that has a container of paint hooked to the top rung, we can imagine the consequences of the objects falling. They could potentially damage any obstacles at ground level, including your toe. The more massive the object and the higher off the ground it is, the greater the possibility for damage. The ability of gravity to do work on an object by causing it to fall is known as gravitational potential energy. Figure here shows the variations in a brick's gravitational potential energy depending on its height. In part B of figure, some work had to be done in order to elevate the brick from ground level. The work done to lift the brick becomes the brick's gravitational potential energy. If the brick were to fall, its potential energy would decrease as it fell. According to the law of conservation of energy, the total amount of energy of a system must remain constant. Therefore, if the brick's gravitational potential energy decreases when it falls, its kinetic energy must correspondingly increase. The brick accelerates as it falls, pulled by Earth's gravitational force. We can derive an equation for gravitational potential energy from the equation for work as work is equal to F into delta D, but E g is equal to W and delta H is equal to delta D. Therefore, work is equal to F g into delta H, but F g is equal to m g. Therefore, work is equal to m g delta H. Using the ground as our reference point for measuring the change in height delta H, the expression m g delta H represents the change in potential energy from ground level 0 to a height h. At ground level, E g is equal to 0. So, delta E g is equal to m g delta H, where m is the mass of the object measured in kilograms, g is the gravitational constant measured in Newton per meter, and delta H is the change in height of the object measured in meters. Near Earth's surface, the gravitational constant g barely changes. For simplicity's sake, we will use g is equal to 9.8 Newton meter when dealing with objects near Earth's surface. Power. The time rate at which work is done by a force is said to be the power due to the force. If a force does an amount of work W in an amount of time delta t, the average power due to the force during the time interval is W upon delta t. The instantaneous power P is the instantaneous time rate of doing work, which we can write as P is equal to dW upon dt. The SI unit of power is joule per second. This unit is used so often that it has a special name, the watt, after James Watt, who greatly improved the rate at which steam engine could do work. In the British system, the unit of power is the foot-pound per second. So friends, here we come to the end of our discussion, and therefore we sum up. In this lecture, we learned that a system is closed if the amount of energy contained in it is constant. In a closed system, energy is transferred from one form to another, but there is no energy transfer from a source that wasn't originally in the system. This constraint keeps the total energy constant. Work is the transfer of energy. Work is done when a force acts on an object, causing the object to move in the direction of the force. Kinetic energy K is energy associated with the state of motion of an object. The faster the object moves, the greater is its kinetic energy. When the object is stationary, its kinetic energy is 0. The ability of gravity to do work on an object by causing it to fall is known as gravitational potential energy. The time rate at which work is done by a force is said to be the power due to the force. So that is it for today. In the next lecture, we shall be discussing about Newton laws. Thank you very much.